Hello, and welcome to the evening edition of Answer Everywhere. Today we're taking a look at Kubeflow Pipelines. This is part of the larger Kubeflow project, which is basically trying to make Kubernetes into a place where you can do all of your machine learning stuff. So we're all familiar, well, many of us are familiar with Kubernetes as a place to run essentially web services. Machine learning is also about things like batch jobs and pipelines of various kinds of jobs, and traditionally, that's been more the arena for maybe like high performance computing or things like Slurm or whatever that uh, that scheduling software is called. And I think the idea, at least in theory, for Kubeflow, is that they want to make the Borg-like thing, Kubernetes, into a thing that is also very good at being able to work with your machine learning workloads. I haven't used it much myself. I played around with it. I installed it. I clicked around, but people seem to like it. And I think for the first time ever, we have a um, a contributor to the project who's hopefully on the chat, and that is Raquel. So, Raquel, you're around. Let me know. And so let's plow along. So here's GitHub. Um, the thing I notice is that we have a lot of different languages here. We have Go, which I expected it to be mostly Go, but it's mostly Python. Also TypeScript, presumably for the front end. JavaScript, I don't know for what, for whatever, I guess, can't fill in with TypeScript. There's some Jupyter notebooks. Those mainly might be things like examples. Um, and then a little bit of shell, presumably for kind of glue operations. And So I'm going to guess, given the distribution here, that Go is mainly going to be for interfacing with um, with the Kubernetes APIs. Python is the lingua franca of data science, machine learning these days. So I'm guessing a lot of the Python stuff is going to be um, I don't know. We'll see. I was originally going to say something machine learning-y, but I'm not sure really how much of that there will be in pipelines. So pipelines, at least in theory, should be about, um, pipelines having a essentially a group of of jobs that all relate to each other that form some sort of graph. And we've seen this pattern of several times now on this channel, including we've looked at Argo CD and a few other CD pipelines whose names I'm kind of blanking on. But we've also seen similar patterns show up in things like compilers. Hello, Raquel. So Raquel is here. All right, cool. So let's dig into the code. Um, the I'm not sure where the coolest stuff is. So API is often a useful thing when we are looking at Kubernetes stuff. Backend is presumably going to be useful. Components and front end, the Kubernetes platform, and manifest. So this is a Kubernetes thing. So manifest is presumably going to be all of the YAML that you need to string together to deploy deploy pipelines. Proxy is going to be some sort of proxy. I don't know what kind of proxy or how important it is. I'm going to skip it for now. Samples. Let's dig into samples. SDK, I don't know. And then third party and tools, I will just totally ignore. Let's see. Let's take a quick look at the README to make sure I'm not missing anything, at least conceptually. So we have end-to-end orchestration, enabling and simplifying the orchestration of end-to-end machine learning pipelines. So I'm not sure what end-to-end means, but presumably one end is you have a bunch of data and you're training a model on it. And another part of it will be you have that model and now you want to make Taylor Swift deepfakes to post to Twitter, which is apparently the thing that everyone's doing these days. I'm sorry, to post to X. And at some point, you're going to get some output to your machine learning models. And you may need to serve a model. Let's say like you are Google or whatever, and you're training Bard, and you have to deploy Bard as a service. And then when people make requests to you, that's going to go out to some GPUs or some uh, tensor machines or whatever those things are called, and serve data. But I don't think pipeline is in charge of serving. I think there's another component, and maybe Raquel, you can tell me if that's correct. Um, and also easy experimentation, making it easy for you to try numerous ideas and techniques and manage your various trials and experiments. So I think one thing that Kubeflow does is like hyperparameter. But I don't know if this is part of Katib. I think that's a different component. So we can see here on the side different components. So Kubeflow Pipelines is one of them. Notebooks is basically serving. Um, if you're familiar with Jupyter Notebook, or I think there was another Python notebook that was around for a while, but basically serving like a version of Jupyter Notebooks that's integrated with the rest of your Kubeflow stuff. And so the idea is that if you're some company, then your team's interface to all the machine learning stuff will be via Kubeflow. And so the notebooks, I think, are there to have an entry point for them for the like machine learning engineers, so they don't have to think about things like DevOps or ML ops. And then there's a dashboard. Pipelines is what we're looking at, and then Katib is, I guess, for uh, hyperparameter stuff as well as maybe something else. Provisioning, machine learning, project for automated machine learning. Okay. Early stopping, blah, blah, blah. Okay. I don't know exactly how these different parts fit in because I'm not close enough to the machine learning world to know like when these things require different jobs or different levels of expertise in various domains. And then we have a trainer operator for fine-tuning scalable distributed training of machine learning models. So this is maybe you already have a model and you want to fine-tune it to your specific use case. Like you have a document model and you want to fine-tune it to, and you're a law firm and you want to fine-tune it to law documents about mergers and acquisitions or whatever. Okay, but the part we're focusing on is this pipeline. And let's look at we can have a quick look at the API. You can get experiments. Yeah, so let's look at the UI. This is a good point. So screenshot maybe? Maybe something like this. Well, maybe we'll find a screenshot. But uh, there are experiments that you can see if you click on the main UI. You have pipelines, and then you have the ability to run, I guess, versions of a pipeline or versions of an experiment. There are, I guess, a job is presumably like a one run of the whatever, and then we have, you can get the pipelines, do all the CRUD operations with pipelines. You can upload some stuff. I'm not sure what we're uploading, if that's artifacts or something else. Health C is a standard googly thing for essentially exposing scrapable web endpoints that will tell you, like, is the job healthy? And whatever this is, more experiment stuff, page tokens, page sizes. All right, cool. All right, so that just gives us a quick sense of what the API is about. All right, now let's dig in. I was going to look at examples or samples rather. Contrib core tutorial. You can run the samples. I think I just want the simplest sample, maybe core. Caching data flow, hello world. That looks promising. Loop output, multiple outputs, parallelism, recursion, retry, secret, sequential. Look at sequential. No. Let's look at train until good. Where did it go? Train until good. .py. So we have a Python file. It's a little bit surprising. I was expecting some YAML that involved Python at some point. Um, so KFP should be Kubeflow Pipelines. We're going to import components, DSL and client. I guess DSL, maybe we're not going to get YAML. We're going to get a Python DSL. And I'm missing something from the chat. Let me pop this out. I accidentally covered up my chat window. And Mikhail is saying you can always use the pipeline for orchestration, serving work. Okay, so you can, I guess, set up the pipeline to essentially set up your deployment of services. It sounds like. Although, why did that go away? All right, window. Roll back through it. No. All right, so we are importing some stuff. We're getting some data sets. Stop this, GitHub. Whatever that is, don't do it. And can I close this? Can I close it all the way? GitHub. Okay, so we're getting some data sets that we're just grabbing from some URLs, like the Chicago taxi data set. We're also getting XGBoost. I don't know what that is, but it's something about training on CSVs, comma separated value files. And it's boosting something. Is it like add a boost or something? I don't know. Let me just look up XGBoost. Open source software library that provides the gradient boosting framework for C++. Okay, so we're doing gradient boosting. What is gradient boosting? Based on boosting in a functional space where the target is pseudo residuals rather than typical residuals used for traditional boosting, gives a prediction model in the form of an ensemble of weak prediction models. Yeah, I don't know why this is called boosting, but I think this is basically what boosting is. You have an ensemble, as in like a collection, almost like a statistical ensemble of weak prediction models, basically things that kind of semi suck, but hopefully suck in an uncorrelated way. And then you aggregate over them, and hopefully the uncorrelated errors cancel out and the signal shines through. And I think that's generally what boosting is an ensemble meta algorithm for primarily reducing bias and variance in supervised learning. Okay. 1988. Can a set of weak learners create a single strong learner? Good question. And the answer is yes. That seems like one of the really natural things to do. There's lots of stuff in machine learning that seems like, I don't know why you would try that trick, but boosting, I think, it seems like a really natural thing to do. All right, and then we're getting some Panda stuff. Whatever drop header is, calculated regression metrics, blah blah blah. That's all well and good, but we get this DSL graph component decorator. Presumably, it's part of the DSL from the syntax, and presumably it's a graph component. Let's see if that's right. This recursive subpipeline trains a model, evaluates it, calculates the metrics, and checks them. If the model error is too high, then more training is performed until the model is good. So this is just doing what it says. We have some target, and while model is not good enough, keep going. So training until low error is a function that's decorated using this graph component thing. Takes a starting model, training data, and true values. I don't know if this is a generic API for a graph component, like if that's something that everyone has to implement. I'm not sure. But the model is going to be, we're going to do XGD boost train on CSV op with the training data and the starter model. I guess label column 0 means that the first column is going to be labels of, as opposed to data. The objective will be squared error. Reg, I don't know if that's modifying squared error in some way, or if squared error is just in the reg namespace. But presumably they're going to calculate the error and square it, which is a normal thing to do. And they're going to do 50 iterations. It seems low to me, but maybe I'm just used to things that require more iterations. And then I guess dot outputs means it's going to output something. What's it going to output? I'm not sure. Actually, this is Python syntax for indexing into a hash table or a dict keyed by a string, and the string is model. So I guess that XDG boost has some going to maybe return a result of the outputs, and we're going to just get the model from it, something like that. And then the prediction is we're going to call the XDG predict on CSV thing, with the training data, the model that we got from here, and we still have to tell it that for the CSV, the first column are labels, and we get the output, and then we calculate some regression metrics. And I don't know if I don't know in what sense of regression this is, if this is like linear regression or just some more generic sense of the word regression. And then we check some metrics. I guess we got the metrics here. We calculated them rather, and now we're going to check them. And we've got this DSL thing. We've got a DSL condition that says the mean squared error should be bigger than 0.01. I guess we want that to be small. So I guess this is saying that if the error is bigger than 0.01, then we'll recursively call ourselves train until low error. Now I'm getting a big yellow thing says YouTube is not. Let me check my video quality here. Okay, I still seem to be live, but okay. So it's saying it's buffering. Let me pause my video for a second and see if I can improve the situation. One moment. Okay, I added a second network connection, so maybe that'll be good. All right. Okay, so this is a pretty straightforward example. We have this other thing down here. We have a DSL dot pipeline. And this is the train until good pipeline. And we're gonna get the training data again. Did we already get the training data? Oh no, we just defined a function that accepts training data as input. But now for the pipeline, we're gonna get the training data from the CSV file, transform it in some way using pandas. I guess we'll get some sort of pandas table. And then we'll do initial model training using XCG Boost. Basically, I guess the same sort of thing that we did before. Now we're going to recursively call train until low error with the first model. And I am being told that OBS disconnected and reconnected, but I seem to still be going, so I'll assume that's the case. Okay. All right. So that was useful for me. Now I have a more of a sense of how things are going to go. So here's the API. Do we care about the API now? I'm not sure. Let's pull this out. And we have Go and Python. Cache key pipeline spec. Cache key is going to be some cache key. We're going to pipeline spec. This is going to be essentially the Go version of the YAML, I think, that defines what a pipeline is. And we have primitive type. And the primitive type can be an int, a double, or a string. I'm not really sure what this is about. Pipeline task trigger policy. Task state. Okay, so this is essentially a this is an enum, sort of like a state machine for what state is where is the pipeline? Is it pending? Running driver succeeded. Running executor. I don't know what the difference between the driver and the executor is, but maybe one one drives, one executes. Maybe the driver is like um, the overseer of the operation, and the executors are like the workers, and you might have multiple executors. I'm not sure, but it could have some state like succeeded and or whatnot. Okay, then we have task state, same as before. That's pipeline. This was pipeline state. We also have task state, and task state has um, many of the same things. And here's a pipeline job. This seems fundamental. So it has a pipeline job is what? The model is that it's got a state, it's got a size of the cache, which is a little bit surprising, but I guess not entirely surprising. It's got unknown fields, and a name, a display name, which could be different from the real name. The pipeline spec, which is basically going to be more YAML. That's going to, I guess, specify what the pipeline is, labels, and a runtime config. This is kind of standard Kubernetes stuff. I see some proto reflection stuff. Here's the pipeline spec. And again, we get a state, a size cache, and unknown fields. That seems to be maybe just generic metadata, at least in this uh, repo. And we have pipeline info, a deployment config of the pipeline, which is a deployment spec. I'm not sure if this is like a standard Kubernetes deployment spec, but maybe it is. And if it is, then that makes, I guess, essentially the pipeline's a container or group of containers, more or less. We have an SDK version, some components, the map of name to definition of all components used in the pipeline. So name to definition. I don't know what that means, but basically some lookup place where there's some name registry that's implemented as a hash table. Morally speaking, seems to be what that is. Okay, so this is just basically like reading Kubernetes YAML, and it's not the most exciting thing. I don't know if Python's any more exciting. We have generate proto.py, generate a underscore pb2.py from a proto file. It's just some function to invoke the protocol, the protobuf compiler. Okay, so I think that I think API is not the place you want to hang out. Backend might be interesting. I'm gonna guess backend API is not so fascinating. But in backend we have an agent / persistence. I think this notation in GitHub always means that there's an agent folder. The agent folder is empty except for a single folder called persistence. And I'm going to guess that means that this is essentially for interfacing with like Kubernetes volumes or databases or whatever. We have an API server, which is either going to communicate with the Kubernetes API server or it's going to serve the Kubeflow API. Cache, presumably going to be in charge of caching things. I'm kind of curious what they're using for a cache. Common, I don't know what will be there. CRD those are going to be custom resource definitions for Kubernetes, things that the Kubernetes system needs to be aware about in order to let the magic of the Kubernetes control, reconcile loop, handle pipeline backend information. Let's take a quick look in common just so that we see what might be here. And it's mainly the API server. We have experiment client fake, presumably just a test fake. pipeline client, fake, et cetera, recurring, run client, run client. So experiment and pipeline and health Z, I recognize as all being parts of the API, which makes sense because we are in the API server / v2 folder. Recurring and run are probably also part of the API. Let's pick one victim, I guess maybe pipeline, and take a look at it. The pipeline interface. These are just really the CRUD operations. So create pipeline and version, get, delete, list all. And a pipeline client struct has an API client, which if we could find this string. So the API client, I guess, is being imported from pipeline client in the pipelines project, as opposed to maybe, I thought it was possible it was a more general purpose Kubernetes API thing, but it seems specific to this project. And an auth info writer. Auth info, I'm going to guess, is authentication info. And I'm going to write something about the auth stuff. We have this new pipeline client, which is basically the Go version of a constructor. We get a new HTTP runtime from the API server, passing in the client config and I guess debug status. Debug is a bool, presumably yes, I am debugging, or no, I am not. Check for errors. If all is good, we call API client new on the runtime, which we got up here, and some stuff about default string formats. And then we return the API client, wrapping it in this pipeline client struct. So that's not so fascinating. This is all kind of like so far. This is all boilerplate that you may recognize from very similar to what we saw when we were looking at the Kubernetes repo. The CRD controller is maybe a little bit more interesting. We have a scheduled workflow and a viewer. I'll open those up. We'll get to them. Here's the backend source / v2 cache utils command compiler. I guess let's look at compiler. Let's look at component. I'm not sure what the driver is. Expression is maybe something about the, what's the word? The DSL. Object store is going to be something about objects and storing them. All right. We do get a README, which is nice. But I think this is mainly for developers, like how do you set this up, and not so much what's going on in this directory. Okay, scheduled workflow. We have main and controller. Which one's more interesting? Let's look at main. We're going to parse flags, set up some signal handling. There's going to be some Go channel stuff, it looks like. Build config from flags. Okay, this is just all set up. And then I guess ultimately we're calling controller run. Let's look at the controller. Importing a ton of stuff. Lots from the pipelines project, from the CRDs, and lots of stuff from various things under the CRD. CRD / package seems like a cool place to be if you're into APIs. So controller has a Q client, which I think now is the general Kubernetes client. What was that? Client dot. So what is client? I'm not sure. All right, so we've got this Q client. We've got a SFW client, which is, I guess, a scheduled workflow client, and a workflow client. So we've got this controller's got, it's going to talk to these three things: the workflow API, the scheduled workflow API, and presumably Kubernetes. We have this comment: workflow is a rate limited work queue. Sorry, work queue is a rate limited work queue. So we are a work queue. We're essentially a queue of work that needs to be done, like a to-do list. and it's rate limited. This is used to queue work to be processed instead of performing it as soon as a change happens. This means we can ensure we only process a fixed amount of resources at a time, and it makes it easy to ensure we are never processing the same item simultaneously in two different workers. Okay, so we've got some rate limiting service. Um, Interface to generate the current time. Okay, so we've got some time interface. Generate the current time, like a clock. Not sure what that means. And then we've got some time zone, and that's all the controller is doing. That's all the controller has as its model. This get new controller is just going to set things up. But what is it? What are the behaviors? The controller can run. Run will set up the event handlers for types we are interested in. Okay, so we've got some event handlers. So presumably we're going to get some events, and we register for types we're interested in. So it's kind of like subscribe, pub sub style, as well as syncing informer caches and starting workers. I vaguely remember learning about maybe informer caches before. Look up informer cache. Deep dives into Kubernetes informers. I think this is how Kubernetes talks to, um, yeah, handles watch. Yeah, the vital role of a Kubernetes controller is to watch objects for the desired state and the actual state, and then send instructions to make the actual state be more like the desired state. So this is basically the standard control system situation, and it's implemented somehow with informers. In order to retrieve an object's information, the controller sends a request to the Kubernetes API server. However, continuous polling for retrieving information on the resources can degrade the performance of the API server. To stay informed about when these events get triggered, client-go provides informers which solve this problem. Informers query the resource data and store it in a local cache. Once stored, an event is only generated when it detects a change in the object or resource state. Okay. So what does that mean? The informers query the data and store it. So we're still querying the data. I don't know how that's different from polling, but there's some layer of indirection. I don't remember where the informers live. We have this diagram. So this is the Kubernetes API server. I don't know what the reflector is, but I guess a reflector is going to say, I want to list and watch something. Um, so that's like calling watch on bash, or maybe it's like subscribing to, I think it's like calling watch on bash. So if I like do this, no, I'll get a terminal around here. If I do like watch free, it'll just call free every 2 seconds. And then that essentially polling. So I think that's the sense maybe in which a watch might happen. So at any rate, it's going to watch for something. It's going to subscribe to some stream of events so that it can look for changes. It's going to add objects to a Delta FIFO queue, I guess a queue of Delta presumably changes to the thing that it's watching. And then the informer, it looks like, will pop objects off the queue and add them to an indexer, which is some thread safe store. And I don't know what a square versus a triangle is. Triangles are deltas are traditionally triangles. I'm not sure what the difference between these two things is, but at any rate, the informer also seems to dispatch event handler functions. Um, I guess it'll let you know when something has changed. So when it notices a change, it stashes it, and then also simultaneously tells it's the people subscribing to the informer about what's going on, and then somewhere, whatever this line means, some sort of barrier, um, there are some resource event handlers that do stuff, something like that. That's Bard. Tell me about Kubernetes informers. While it's thinking about that, let's return to the code. Okay, so informer caches. So this controller, the scheduled workflow controller, sets up event handlers and syncs informer caches and starts workers. So um, I closed that diagram, but this is that was one of the entities in the diagram kind of performs all those services. It will block until stop channel is closed. Okay, so it's going to check. It's going to wait for this stop channel to close, at which point it will shut down the work queue and wait for workers to finish processing their current work items. Okay, so it's not going to just abandon the in progress work. It'll let workers finish their stuff. Okay, so defer handle crash. I guess that means that we are going to, I think that when you defer things in Go, the first thing you defer happens first, and the second thing you defer happens next. And so maybe like the last thing that you defer is the thing that you do as finally in Java or whatever. Um, okay, so we're going to handle crash and then we're going to shut down after all of the other code is finished. Then we're going to start the informer factories to begin populating the informer caches. This is just a log statement. We're also going to log about waiting for informer caches to sync. We're going to call wait for cache sync, passing in stop channel. See workflow client has synced. That seems to be a bool of some type. I don't know. Maybe these things have to wait for each other. Wait for the caches to be synced before starting workers. All right. So somehow these all have to synchronize, I think, together. And if there's an error, we error out. And then we're going to launch multiple workers to process scheduled workflows. And threadiness. So we're going to, whatever threadiness is, it tells us something about how many threads. We're going to iterate over the threads, presumably, and create Go routines that are presumably going to wait until some condition. And I guess they take a run, they're going to take a run worker, they're going to be worker threads. And something about time seconds and stop channel. And so this might be where the it says that it's going to check that but their stop channel is closed, and this might be where that happens. It's named consistent with that. I don't really know wait until does, but I think that's a standard Go thing. I just haven't done that many Go Go routine stuff. And then okay, so we're getting from stop channel. I guess this is what was really waiting for it. Maybe this is just here so that stop channel can communicate with the threads. And then I guess if we're down here, the stop channel has finished getting stuff, and then we're done. And we're just gonna shut. Okay, and run worker. Run worker is a long running function that will continually call the process next work item function in order to read and process a message on the work queue. It enforces that the sync handler is never invoked concurrently with the same key. So we're just going to call next with the run worker thing. And then in queue, scheduled workflow takes a workflow and converts it into a namespace / name string, which is then put onto the work queue. We're going to take a scheduled workflow object and just drop it on the work queue, converting it to a string. The message should not be passed resources of any type other than scheduled workflow. Seems like something for the type system, man. But I guess Go, you're going to give it an object interface. Basically anything. All right, handle workflow will take any resource implementing a meta v1 object and attempt to find a scheduled workflow that owns it. Okay, it does this by looking at the object meta owner references field for an appropriate owner reference, and then enqueues that scheduled workflow to be processed. If it doesn't have one, it will be skipped. Okay, that's fine. Then process next work item is presumably going to read from a queue and process it. We're going to get an object off the queue here. If we're supposed to shut down, then we'll return false. I guess that means don't do more processing. And then this is some something maybe about the thing being done. Yeah, we're going to defer done. That will tell us when we're finished with the item. And then we're going to do what? I guess try to cast the string as an object. And if it's not okay, we're going to forget the object and handle some errors. And then I guess down here is when we're actually going to do work. Whatever the sync handler is, we're going to try to sync again and possibly error out. And there might be different errors. And if we're down here, then we've successfully done some stuff. And then we're going to forget the work queue is going to forget the object. Then we're going to call work queue add after object, which I thought we just told it to forget. A 10-second delay, maybe. Need status changes to propagate. I'm not sure what that does. Whoa, whoa. And then the SWF I think is a client. And so if this client is not nil, we're going to say that we're going to record sync success, saying that we successfully synced some stuff, partially done, syncing again soon, and then return true. This is synchronizing with something or other. Presumably, maybe part of the same informer stuff. Here's the sync handler. Okay, that's enough for me in this file. I want to see some other stuff. Argo compiler and a visitor. So there's going to be some visitor pattern, possibly on the Argo DAG. See if we get any comments. Compile. We're going to give it a job arg. I don't know if that's arg as an Argo or arg as an argument. A pipeline spec and a bunch of stuff. We're going to clone the job and do what? Look at its name, get its root. Yeah. Okay. So if we're down here, we're doing tree stuff or graph stuff. At least on this, maybe at least on the spec, we're getting the root of the spec. Maybe that's not so graphy. It seems like this is all just like setting up YAML stuff. And then down here we're creating this workflow object. And we've got this workflow compiler. We'll take a workflow and some templates and a launcher image. And I don't know what this is doing, but I kind of have the feeling that we're essentially taking some description and programmatically generating some YAML that is starting to, you've kind of like declaratively said what you want your job to do as the machine learning person. And this seems like it's maybe taking that and generating the appropriate stuff for Kubernetes to make that actionable by turning it into specific runs of specific containers at different times or whatever. But I don't know. I'll see if there's any Argo compiler Kubeflow. How does importer work under the hood? Yeah, something about YAML, something about Argo. We looked at Argo before, and I'll put the video in the show comments. Basically, it's kind of CI/CD stuff. I think Argo also has a pipelines product, but if you're familiar with Jenkins, kind of like Jenkins for Kubernetes, but with hipper logos. Okay, so here's backend stores v2/component. We have constants, importer, launcher, launcher, and launcher. I'm going to ignore those. Driver. I was curious what the driver does. Let's see what the driver does. Option struct. Move driver to component package. Okay, so we have options. We have a pipeline, a run ID, component. So I guess pipelines have components. Iteration index. I don't know what this means. Maybe if this is a like something that loops, this is maybe just the loop iteration that we're on. A runtime config, namespace, a task, I guess the task that the pipeline is executing, a DAG execution ID. I don't know what that means. DAG is presumably directed acyclic graph. Maybe if you're in a DAG that there's a conventional way to number the nodes. Right. A container and an executor. Okay, and we can get info. That's not so exciting. Will trigger is a bool, I guess, telling us whether we will trigger something. We have a root DAG, and it's a function. It's going to take a context, some options, and a metadata client, and we'll return an execution. And I'm not sure what it does. Okay, so we're going to defer this thing, which is basically just checking for errors. This to me, I'm not a Go developer, but this looks like a totally different style from the stuff we were just looking at. This looks a little bit more. This looks very like action oriented. Like somebody's like furiously typing this out. Whereas the other stuff looked very uh, reflective and thoughtful. Maybe, I don't know. Okay, so we're going to validate root DAG, check for errors, and we've got some pipeline spec. Rename GCS output directory to pipeline root. We've got this runtime config. We're going to get GCS output directory, whatever that means. I don't know. Check that the pipeline root is not the empty string. And if it's not the empty string, we've got this REST in cluster config. I don't know what that is. Maybe REST is in like a RESTful interface. And then we're going to get a new config. Oh, okay, so we're going to get a Kubernetes client, I guess, from the REST for the REST API. Maybe. We're going to get a config map. And pipeline root is just going to be the default pipeline route called on the config map that we got, I guess, from some Kubernetes YAML config, I think. And then we're going to call get pipeline on what? On the pipeline route? Yeah. So I guess the thing that has information on the pipeline is maybe the metadata server, which I think basically means it's just some stored under some key in etcd. So essentially I think my mic is floating upward. I think we're querying the metadata server for pipeline information. And this is essentially just a get, a call to the API. And then this validate function is a series of if statements, just checking for what things are the empty string. A container. Yeah, okay. I have no idea what's going on here, but we have got some DAG, that's for sure. Do I want to know what a container is? Not sure. Maybe let's look at the functions. Can I do just a grep for functions? Try Emacs. Before we try Emacs, let's find out where we are. Whatever. I was looking at driver, but let's move on from driver. Let's see what else is here. So I think we looked through here. This is I did a search for container accidentally. Expression. Let's take a look at what expression is about. I think I had thought that maybe this was about the DSL, but we will see. We have this new function. We've got cell, which is some like a Google security markup thing. Maybe I'm thinking of SEL. Common expression language. Common expression language implements common semantics for expression evaluation, enabling different applications to more easily interoperate. Key applications, security policy. Organizations have complex infrastructure and need common tooling to reason about the system as a whole. Protocols, expressions are a useful data type and require interoperability across programming languages and platforms. Shell evaluates in linear time, is mutation free and not Turing complete. This limitation is a feature of the language design. Okay, so I never really knew what Cell was about, but I think now that I'm looking at this, it seems to be about we want to describe some uh, essentially like a program in a pseudocode, and we want all of the languages that we use, like Python, JavaScript, TypeScript, Bash, whatever Cell supports, to have the same interpretation every time of how that program is going to evaluate. And the programs that we want to do this to are hobbled in the sense that we don't have things like infinite recursion, infinite loops. They're not Turing complete, so that you are there's a bound on the complexity of what it can be expressed. So I think that's what it's about. So here's an example: Boolean conditions, account balance. Actually, I can see this being useful. Account balance is bigger than or equal to transaction dot withdrawal or account dot overdraft protection, and account overdraft limit is greater than or equal to account withdrawal minus account balance. So that's useful because you could imagine writing, being in a bank or trading, like a trading firm, and you have account balance implemented in each of the languages you use. Let's say you're like Google and you have four major languages. Then you want to make sure that everyone has the same interpretation of what the account balance is. That's I think a good example, and they're claiming that Cell is essentially a way to do that. At any rate, we have this select environment and condition environment, and we have Cell declarations, stuff about parse JSON, decals overload. We're gonna maybe overload some stuff. We're gonna parse some JSON. We might overload some stuff. We're gonna declare context proto. Maybe the thing we're cellifying are protos that describe some situation. Select from a protobuf value using a cell expression. Fields of protobuf value can be directly referenced in the select expression. Okay, so we have an AST, an abstract syntax tree, and we're calling E. What is E? E is the expression. On the expression, we're going to, compile it. And we get AST and issues. Issues seems to be like error, but not quite error. We check if there are errors with the issues with the error or whatever. And if there are not issues, then I guess we create a program with the AST, passing in the cell functions. And the functions say overload. I don't know what overload is. I guess we're going to overload this operator. Maybe it's a unary operator called cell parse JSON. And we're giving it some ID, I suppose. I guess. And we get a program back, the program object that somehow embodies the compiled program. Or at least the understood program. And then we're going to call a message to cell map on V. What is V? V is the struct PB. So essentially, there's some struct protobuf file that and this is some proto message. We're going to take the proto message, convert it into a cell map, I guess. Add the protobuf value field that is set and passing in true. Should we add unset fields as default values? I don't know. Somehow we're getting some fields. And if v is not nil, we do some more work. We call protobuf value to text on v, and we get some text. And we set the fields here at string value to text. So I guess this just is recording what the original protobuf was. And then we call program.eval on the fields. So we got this program, and now we can evaluate it as a cell program. And it's going to operate on whatever the protocol buffer fields were, and we get some result. And then we do some stuff with the result. Okay, so I think this is about the DSL. Otherwise, I don't know why I go through all this rigmarole. But this seems to be about evaluating the function. We don't see any, at least here, a definition of what the DSL is. We have an expression test, nested map one bool. We get to see, okay, so we pass it in a struct pv new string value, hello world. We get the expression hello world back. And then I guess this is checking that there's a round trip, that the output matches the input. Where's the struct pb? Seems to be a well-known protobuf thing. Struct pb contains generated types for Google protobuf struct.proto. The messages, that is, value, struct, and list value defined in struct proto are used to represent arbitrary JSON. The value message represents a JSON value. Okay. So here's some example JSON. And we are going to turn it into a proto call buffer by calling new value. And what? Is it not going to show us the proto version? All right. Well, it's some way of protofying JSON, I guess. That's v2 expression. So where is the DSL? Driver config. Let's see if we can just do a search for DSL. I mean, we can do a search. Let's see if the search for DSL is fruitful. We have dsl.py. Look at dsl.py. But before that, let's take a real quick look at object store. Open bucket, bucket prefix. I wonder if we're just planning on using, yeah, like cloud buckets, S3, presumably the Google buckets, whose name I forget, GCS maybe. All right. What's this? DSL.py. Dev DSL, command group for compiling DSL to IR. IR presumably is intermediate representation. So what? Click group, commands compile, import click. What is click? A simple wrapper around opt parse for powerful command line utilities. Okay, so I think that's just a command line, whatchamacallit. And we're from KFP CLI, we're importing compile underscore. Do we have a compile? All right. So we have a bunch of click options, which we'll ignore. Select pipeline or component func. Select pipeline or component from module. What's actually doing DSL stuff? Okay, so here, there seems to be some DSL thing that I'm missing. Did I just miss a file? Yeah, here we go. Okay, this is where I was before. All right. Let's take a quick look at things like base component, component decorator, component factory. I don't think we have to dig too deeply into this DSL, but might as well look a little bit into it. Pipeline task, structures. I'm just going to essentially pick these at random, not attempting to be thorough in any way. So here's executor or executor. I don't know how you like to pronounce it. Um, executor, executes Python function components. Okay, so we have the init's going to take an executor input. It's going to take some dict essentially, and a function to execute, which is either a callable or a Python component. And I don't know what the executor input is. We've got this container task root thing. We're going to set some reference to input artifacts from the something. Essentially, this. I don't think any of these come from the input, do they? It's essentially a dictionary from strings to either artifacts or lists of artifacts. And similarly to output artifacts. And then we're going to call assign input and output artifacts. Is right here. And then we're going to do this return annotation thing and set the executor output to some dict, which I guess you can inspect when it's done executing. And assign input and output artifacts is going to iterate over the input and get the artifacts from essentially keys in some dictionary. And it's just going to assemble some stuff. And all of that's fine. That's enough for me for the executor base component. Base component is not intended to be used to construct components directly. Use KFP DSL component or KFP something that gets cut off by GitHub. You're going to give it the name of a component and a component spec. Now, what I don't know is the spec the same as it's a protobuf? Okay, so this is beginning to make sense. So the DSL is really a backdoor to specifying things in a protocol buffer, I think, which makes makes sense for something that Google is building. So that's how I'm going to think about it. At least if you know Kubeflow pipelines or Kubeflow, and you know that that's incorrect. Basically, what you want to do. Remember at the beginning of the video, I was a little bit surprised that the DSL for Kubeflow pipelines was taking place in a Python file, right? What is it? Run until good. Let's look at that again. It's like run until good. Was until good. How about train until good? Okay. And so this DSL isn't really much. So what it's doing is it's just uh, setting component to be equal to some function, setting pipeline to be equal to some function. And I think morally speaking, what's going on is there's some protocol buffer that describes what a pipeline looks like, and this is mapping the fields of that protobuf to some specific Python functions. I think is what's going on, and then everything kind of in the DSL implementation is it seems to be like it's going to be about setting up that mapping. Um, and maybe to see if that's really the case, we should look at the protocol buffer, this spec. Python file. Oh, that protobuf. Oh, no, not protobuf. Proto pipeline spec.proto. This looks promising. Okay, so we have a pipeline job. I I personally like protobufs. Um, I think it's a compact way to see an API, at least much more compact than like the Go files that kind of provide the same information but with a lot more boilerplate. All right, so a pipeline job, a pipeline spec. The pipeline spec has pipeline info, which is some metadata, a deployment spec. I think maybe we looked at this or something similar. SDK version, schema version, a runtime parameter, which is what? We've got a primitive type, enum, maybe return value, required field, the type of the runtime parameter. I don't know what runtime parameter means, but then a default value of the runtime parameter. And then we have a map of name to definition of all components used in this pipeline. String to component spec. Whatever a component spec is, the definition of the main pipeline is going to be the root and the default pipeline route. Component spec has input definitions, output definitions, and an implementation, which is either a DAG spec or an executor label. Okay, so this is starting to look and feel like defining functions, right? So functions take some inputs, they have some outputs, and they have some implementation. Now, this is not quite a function because we are dealing with a DAG, a directed acyclic graph. So I don't know what these input definitions are. You might imagine that like if you have like 3 functions to execute, then you have like a list of 3 tuples. The first tuple are the arguments to the first function. The second tuple is the arguments to the second function, and so on. Or there might be something else entirely. But it seems like these are the sorts of things that you would need to describe a family of functions that are interrelated in some way, such as by having dependency relations on one another. And then we have a DAG. A DAG contains multiple tasks. The DAG spec has a map from string to pipeline task spec tasks. And then we have outputs, which defines how the outputs of the DAG are linked to the subtasks. The outputs of the DAG. So I'm not sure if we're recording the outputs of each node of the DAG or if these are just the outputs of the final thing that happens in the DAG. And then I guess let's look at DAG output spec. Definition of the output artifacts and parameters of the DAG component. We have an artifact selector spec, which selects a defined output artifact from a subtask of the DAG. So it sounds like the DAG nodes, or presumably is what they mean by subtasks. It sounds like they, wait, hang on a second. It sounds like they have their own outputs. We have a reference to the producer subtask. So I guess the subtasks are keyed by strings. And then an output artifact key, which is the key of component output specs artifacts map of the producer task. Some task produces some output, which is some artifact. And then I guess this is the artifact key that it produces. And then we have the DAG output artifact spec, which just has a bunch of artifact selector specs. Okay, so I said above here that I wasn't sure if this is just the final output or if it's the output of all the intermediate ones, and it's the output of all the intermediate ones. And at least that's what it seems to be the case. And I had said before that maybe it was, you could imagine something where like you have a list in the first tuple is the arguments of the first function. And similar to this, for the outputs, the first tuple might be the outputs of the first function. Um, that would be naive because then there's a list is linearly ordered, um, and a DAG doesn't have a linear order necessarily. So how do you deal with that? The way you deal with that is you just have keys into some data structure, and you associate a key with each of the nodes. And so if you want output from that node, you look it up in some dictionary or map or whatever you want to call it, some linear time lookup hashy data structure. All right, so that's how we're getting the outputs. Presumably something similar for inputs. We also have a parameter selector spec. Selects a defined output parameter from a subtask of the DAG. I'm not really sure how an output parameter is different from an artifact, but maybe it's like training parameters or something like that. And more selectory things, more output-y things, component input specs, parameter specs, component output specs, parameter specs. Let's look at this parameter spec. We have a primitive type enum, specifies the input parameters type. So there's some input parameter, like I don't know, some you might have a function, I guess, that takes an int. And I think this is where you declare that it's an int or a string or something else. And then the output parameter has a type. And then there's a description for the output parameter that doesn't exceed 1024 characters. And then you might have some artifact output. And you have a task input spec, which has an input artifact spec. So you're going to pass it some artifacts. Like I think this might be where we saw in the training tool good that you were like passing CSV files for training. That CSV file might be an input artifact. But we also, inside the input artifact spec, we have a task output artifact spec, which is the name of the upstream task, which produces the output that matches with the output artifact key. Okay, so I think that one man's ceiling is another man's floor. So the floor, the output of the thing that came before is going into the next thing, and so I think this is saying that the we're looking for what our input is, and this is the thing that came before that gave us the output. I think is what this is about. And then the input, I guess, has a kind, which is either an output or a component input artifact. So it says pass the input artifact from another task within the same parent component, or pass the input artifact from parent component input artifact. I guess you could receive your parent's input rather than their output. And then we have an input parameter, which could be from an upstream task's output parameter, or it can be from a runtime value, which can be either determined at compile time or from a pipeline parameter. Okay, so this is more input output stuff. What I don't see yet is like which function are you calling? Maybe that's part of task. Do a search for task. I'm not sure. But we are on pipeline spec. Maybe there's another proto that describes. This is cache key spec. It has caches, containers, and artifact name list. Just grab this and look in Emacs. Here's all the messages. We have pipeline job, runtime config, DAG spec, component, blah, 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 inputs, outputs, iterator policy, trigger policy. So there's some policy that defines how, like, I guess when things are triggered. There's some iterator policy, presumably how we're going to iterate. Iterator related settings. Okay, so you can set a parallelism limit. And oh, we were in iterator policy. Is this just recursive iterator policy? Iterator policy. Oh no, that's the TypeScript file. Okay. Items spec. Is that interesting? Pipeline info, artifact, lifecycle. I feel like I just subdivided my. Okay, exec resource spec, envar importer, exec spec. This is I think by far the longest protocol buffer file I've seen. Executor output, platform spec. So here's what I think. I think that this is all an elaborate ruse to specify everything in the protocol buffer. It seems like this protocol buffer file is really encoding all of the behavior of Kubeflow pipelines. And then, well, that's completely inappropriate because the data science team doesn't want to have to think about protocol buffers. So we define some mapping from the protocol buffers into Python. And then there's like a Pythonic way to define the pipeline, but you don't have to worry about Python being so slippery and kind of having an unconstrained type system because you lock the Python's behavior is stabilized by the stable behavior of the protocol buffers, and you ensure that by using cell to make sure that you have like a more formal model that guarantees that whatever you do in Python is ultimately going to be definable and understandable using this cell mapping to the protobuf. I think that's basically what's going on. At least like this. I mean, this is my first time really digging into this project, but this is what I'm seeing, and that makes sense because I've been playing around with machine learning stuff on for my own stuff, and the libraries and stuff I see on GitHub that are or areas where like mistakes really matter. They're full of bugs, is what I found. Like shockingly so, and I think a big part of the problem is that Python's just kind of like a slippery language. It's a language that's designed to get for it. It's easy for people to get started, which means that it doesn't error out. It's not unforgiving in the way that something like maybe C++ or Rust or Haskell would be. But the trade-off there is that if it's easy to not make mistakes, it's kind of hard to guarantee that mistakes aren't made because because it's so forgiving. It's kind of like building something with Play-Doh. It's easy to work with and mold, but it's not necessarily going to hold up a bridge. And so this seems like kind of what they're doing is by specifying so much of the behavior as opposed to just like the data model, by specifying so much of the behavior in the protobuf, it seems like they're essentially using the C type system or the protobuf type system as a way to give rigidity to the Python type system. Or at least that's my interpretation of it. I don't know if anyone who works on the project would agree that that's what they're doing, but that's kind of what I see. I think it's kind of cool. But this is an absolutely enormous protocol buffer file. I don't even know if GitHub is showing me the whole thing. Are they? Yeah, I guess they are. All right. I'm not going to go much further into this, but I think that this is probably a place to start. I'm not sure this is actually literally the longest one I've seen. I've seen some long ones, but um, but there's a lot going on here. Maybe let's take a look at some of the things like value. A value is either an int, a double, or a string. A runtime artifact. I don't care so much about that. Let's see if we can find iterator. Iterator policy. We do have these policy things, and some of them are short. Message iterator policy. Yeah, I think this is just recursive, unless I'm missing some like difference in spelling. Did we look at retry policy? Max retry count, etc. And what about iterator? Iterator supports fanning out the task into multiple subtasks based on the values of the input artifact or parameter. The current task will become the parent of all fan out tasks. All right. Okay, so output artifacts with the same name of each iteration will be merged into one output artifact channel. The output parameters with the same name. Okay, so this is just parallelizing stuff, and you become the parent of the things that you spawn. Trigger strategy. When the task will be ready to be triggered. Trigger policy, caching options, pipeline task spec. If you see anything like implementation, component spec. Okay, we saw that before. DAG or we have the selector expression of common. This is like a CEL thing. Parameter expression selector. Yeah, I feel like I don't quite understand how the Python functions map into map onto this proto definition, but I think that's what's going on, and I'm not going to dig too much into it further because we've been here for a while. But I will try to close out the rest of these files and see if there's anything interesting. Here's component decorator. This should be the decorator that goes that is used to define a component. A decorator for a Python function based components. A KFP component can either be a lightweight component or a containerized component. If target image is not specified, this function creates a lightweight component. I think this is basically answering the question I just had of how a Python function becomes a proto. A lightweight component is a self-contained Python function that includes all necessary imports and dependencies. The function contains all of its imports. I guess as opposed to, in Python, imports go at the top of the file, etc. I'm wondering if this means that the imports are inside of the function, literally. In lightweight components, packages to install will be used to install dependencies at runtime. Okay, so I guess you specify what things need to be installed. The parameters install KFP package and KFP package width can be used to control how and from where KFP should be installed. If target image is specified, this function creates a component definition based around the target image. I'm guessing image is like a Docker container. The assumption is that the function in func will be packaged by KFP into this target image. All right, so func is a Python function from which to create the component. It should have type annotations for all its arguments indicating how each argument is intended to be used. All right. All right, so if func is none, if we have no func, then we do this func tools dot partial. Is func tools a custom thing or is this a Python thing? Must be Python, right? Functools for functions. There's some kind of functional programming stuff. Maybe partial function application, like currying. I don't know. But we give it some component, a base image, and I guess we're just missing a function. So this means this is like we're binding all of this stuff up into a lambda essentially that we can apply func later, perhaps. And at any rate, if func is not none, then we call component factory create component from func. And now I need to know what this function does. Create component from func. All right, so we've got the packages to install commands. We're going to get packages to install command by passing in a bunch of stuff. We'll initialize these command and args as empty lists. Do some, no. Bug and GitHub. What's that function called? Maybe do some stuff with the target image. Extract component interface on the function. And then we get a component spec. This seems to be the thing I want. I'm going to give it a callable, whether it's containerized, a description, and a name. And we're going to return a component spec. And I guess these functions are all being defined within this function. The first thing we call is inspect signature, which I saw before. I wasn't sure what to make of it, but I'm guessing this maybe means the function signature. Can I go to definition? Oh, I guess inspect signature, is it a type or is it a function? Whatever. Let's try a thing called inspect. How about we just search for def signature? How about just signature? I don't know what this inspecting is. Where does inspect come from anyway? Is it something that's imported? Okay, we're importing inspect. Okay, so maybe that's why we're not finding it. Maybe it's a Python package. Inspect live objects. Signature object represents the call signature. Okay, great. That's what I figured. All right, so we're looking at the call signature of the function, which we need to do because in my theory, we want to convert it into a proto. So we're going to get the signature. It's going to take some, it has type annotations. That was one of the requirements that was laid out in the file we looked at about a minute or two ago. So presumably it's going to say, well, this argument is a bool. This is an int. And then it's going to use it's going to use the obvious mapping from those Python types to the protobuf types is what I'm going to guess is going to happen. And then we're going to call it get name to specs. And that's defined here. Can I open this as in a new tab? All right. So we're giving it the signature and we're going to get the params name we're going to create dicts for input and output, and then iterate over the function parameters. If the name is single output name, we're going to raise value error. It's an invalid parameter name. Okay, I don't know what this means. Then we're going to get the type annotations and check if they're empty, I suppose. Is input artifact or input list artifact, etc. So I guess we're going to check if it's a input parameter of a list of artifacts or something along those lines. And if they are, we're going to say name to input specs, maybe make unique name list name to input specs of annotation func param. Okay, so this is basically handling lists, I think. If it's a subclass of artifact, and then we're going to call make inputs back on something or other. How about a more sane type? If type string equals annotation to type struct annotation. Yeah, I'm not sure. I'm not really sure what's going on. I think it seems like this make input spec is doing a lot of the work. Let's take a look at this function. So it'll take a type annotation, which can be an any, and some inspect parameter. Makes an input spec from a cleaned output annotation, from an output annotation. All right. And again, we're checking if it is subclass of artifact annotation. If type annotations is subclass of artifact annotation, we're looking at the annotation and checking whether it's something that can be considered an artifact, I guess. Then we raise an error. Optional input artifacts may only have default value none. I guess also checking if it has a default value. All right. Vectors and yeah, I'm not sure. There's a lot of indirection, but morally speaking, I think it's doing essentially what I thought what I said it was going to do. It's going to look at the function signature and map it to protos. There's a lot of logic there that's essentially saying under what can these are the conditions under which the mapping is valid. Okay, we're still parsing the doc string. Okay, and so that was really kind of my question. So that's the type information. I'm kind of curious what we do with the function body, but I'm not sure. Inputs, outputs, implementation equals structures, implementations. Structures implementation called with no arguments. Where did structures come from? Yeah, I guess we call component. Is it the same function? I think so. We call structures implementation. I guess possibly with a container or something like that. At any rate, this seems to be where this stuff is happening. And the func tool seems to play a big role. And what was the other one? Inspect. Essentially doing like runtime inspection of what the Python stuff is. And you can look at like if you've used the Python debugger, you can pretty easily from a Python object get all of its methods and its implementation and its all of its state and all of that stuff. All right, this is component factory again, which I think I just closed. Executor. I think we've seen enough executor stuff. Pipeline channel. I think that's probably not so important. structures, maybe, input spec, the type of the input, whether the input is optional, etc. From IR component. So IR should be intermediate representation. What is the intermediate representation? I don't know. Is it just cell? IR component input ticked. From IR component input. Yeah, I'm not sure. I don't think I'm going to quickly find what the intermediate representation is. Let's see if they use cell here at all. Intermediate. What if we do Kubeflow Pipelines intermediate representation? I'll do a pipeline. It is considered IR YAML. IR YAML is an intermediate representation of a compiled pipeline or component. It is an instance of pipeline spec protocol buffer message type. Okay. IR YAML is, I guess, it says an intermediate representation. I'm wondering if they mean the intermediate representation. It's an instance of the pipeline spec protobuf message type. So it's essentially a protobuf, which is a platform agnostic pipeline representation protocol. Basically what I was saying. Considered an intermediate representation because the KFP backend compiles pipeline spec to Argo workflow YAML as the final pipeline definition for execution. Unlike the V1 component YAML, the IR YAML is not intended to be written directly. While IR YAML is not intended to be easily human readable, you can still inspect it if you know a bit about its contents. Okay. Type checking. Hey, look, this is all documented. By default, the DSL compiler statically type checks your pipeline to ensure type consistency between components that pass data between one another. Static type checking helps identify component consistencies without having to run the pipeline, shortening development iterations. So, reading between the lines, they're saying in Python, you don't know if you have a bug or an error until runtime because type errors are runtime errors in Python, which kind of sucks. So we have static type checking. The DSL compiler does static type checking essentially the way I said by converting to a protocol buffer representation. And so the reasoning behind it is basically what I was saying. Specifically, the type checker checks for type equality between the type of data and a component, the type of data a component input expects, and the type of the data provided. See data types for more information about KFP data types. For example, blah, blah, blah. I'll read it. For parameters, a list input may only be passed to parameters with a typing.list annotation. Similarly, a float may only be passed to parameters with a float annotation. Okay, great. This is, this sounds like my theory was correct. And with that, I think I'll leave it there with a quick summation of what I feel that we've learned. So one thing I've learned is, at least from what I see, this protocol buffers thing is the right way to think about what a pipeline really is. That's the explicit representation of a pipeline. They're calling it the intermediate representation. And they describe it as not being like super human readable. And I think that's true. But I also think that if you're like maybe debugging or reasoning about the performance or doing any real like technical planning about Kubeflow pipelines, I think the protocol buffer files are kind of the contract that describe what's going on. And then obviously Python on the front end. We didn't get to the TypeScript or the JavaScript, but I'm going to guess that's mainly display information for data that's stored ultimately in Kubernetes. Um, and and then we saw in the API folders and some of the Go, some of the ways that uh, the um, the control loop worked, watching for changes to things and kicking off workers and all of that kind of stuff. Um, so uh, yeah, and then on the back end, it sounds like they're compiling to Argo. When I had looked at the documentation earlier, I thought that I was under the impression that Argo was like somewhat optional, but it sounds like from the doc I just read that maybe Argo is the for right now. Like thinking of this as a compiler, it's the compiler backend, but that seems generalizable. It seems like you could, in theory, um, if if the Kubeflow people wanted to adopt a different backend. Um, and so, in that sense, I think that the the Argo dependency is maybe one of convenience as opposed to like a technical requirement. And so, I'll leave it there. That's Kubeflow Pipelines. Kubeflow Pipelines. Thanks for watching.